In this installment of my continued coverage of special topics lectures, in which I will be reviewing chapters 2 and 3 and then eventually 4, 5, and all of the rest from the previous semester, I'm going to begin by teaching you how to balance chemical equations, then how to determine molecular formulas or formula weights of compounds, followed by how to determine percent composition. Sounds like a lot, but it's really not too bad. Let's go ahead and get started. So as you should already know from doing chemistry over the course of the entire year, before we can really use chemical equations, we have to first balance them. We do this by adding coefficients in front of each formula in the equation until the total number for each atom type is equal on both sides. Let's go ahead and throw an example at you. I want you to balance the following equations. I'm not going to do them for you, but if you like, you can click a link here to a separate video in which I'll show you how to do them. Now to another problem. When the following equation here is balanced, the coefficients are what? Once again, I'm not going to do it, but we'll let you do it on your own, and hopefully you have enough of a command of this subject to be able to do so. Let's go ahead and move from the subject on to molecular or formula weights. Question: do molecules like sodium chloride have atomic weights? The answer is no. When we talk about the weight of a molecule, which is something that's made of two or more atoms bonded together, we're no longer talking about an atomic weight. We're now talking about a molecular weight, so please understand the distinction. An atomic weight is the weight of a single atom or single type of atoms, whereas a molecular weight is that of an entire molecule, where you have two different atoms or more bonded together. Molecular weights are also sometimes called formula weights or molar masses. Let's take a look at some problems then. I want you to determine the formula weights of each of the following compounds: magnesium hydroxide, which is the active ingredient in milk of magnesia, and isopentyl acetate, whose formula is given here, which is responsible for the smell of bananas. Bananas. Once again, I'm not going to do this for you here, but we'll invite you to click, if you wish, the link here to a separate video in which I'll show you how to do it. Now, one thing I hasten to mention is that I would like you, my students, to remember that both atomic and molecular weights units are grams per mole. You can also use AMU, but for dimensional analysis, you almost always end up using grams per mole. Here's another question. The formula of nitrobenzene is this stuff here. The molecular weight of this compound is how many AMU, or if you wanted to use the other units, how many grams per mole. Once again, I'm not going to do this for you, but we'll invite you to do it on your own. That takes us to percent compositions. You see, we chemists sometimes have to calculate a compound's percent composition, which is the percentage by mass of each element in the substance. Now, to determine this, the percent composition of an element in a given formula, you use this approach. You take the number of atoms of that element in the formula, multiply it by the atomic weight of that individual element, and then divide all of that by the total formula weight of the substance, and then multiply all of that by 100. That's the percent composition of the element. I'm sure that's all very straightforward, right? Let's take a look then at a problem. Calculate the percent composition by mass of carbon in each of the following compounds: cocaine and vancomycin. Cocaine is, of course, very horrible, while vancomycin is a very potent antibacterial agent. Now, I'm not going to do this one for you, but we'll invite you to do it on your own. If you wish, you can click a link here to a separate video in which you can see how this kind of problem is undertaken. I now want to introduce you to this topic: calculating a substance's empirical formula from its percent mass. Now, if you want to generate an empirical formula from a compound's elemental percent mass, here's how you'd go about doing it. First, convert the data you're given into grams for each element. If you're given a percentage for each element, then just assume you have 100 grams of compound and change the units from percentages to grams. Next, convert grams of each element to moles by dividing by the atomic mass of the element. Next, divide each value from step 2 by the smallest of the values from step 2, and then round your answers to whole numbers or simple fractions. Next, if you have any fractions or non-whole numbers after the last step, multiply all of the mole values by the denominator of the fraction, or by the smallest number that will make all of them into whole numbers. And then last, the resulting mole values are the subscripts in your empirical formula. Okay, I realize that all of this stuff is a bunch of convoluted nonsense, but I promise it will make sense as we take a look at some problems. Here's one. Determine the empirical formulas of the compounds with the following mass compositions. Now, I'm going to let you attempt to do these on your own. However, if you like, you can click a link here to a separate video in which I show you how to do some of these on the board or maybe on the dot cam. Now, I have to mention something. You might be wondering why in the world we would ever care about being able to do this. The reason is because there exists a special analytical process called combustion analysis, in which you can take a compound. If I've got a compound I found out in a field or a crime scene or something and I want to know what it is, I can put it into the machine, and the machine will spit out what percent of what elements are in that compound. If I know how to do this process, I can then put those percents together to determine the actual empirical formula for that compound. So that's the reason we actually do this. Whew, okay, good. Let's take a look at another problem then. What is the empirical formula of a compound that contains these percentages of sulfur, oxygen, and chlorine by mass? Having looked at the previous video covering the empirical formulas from the previous slide, I'll let you do this one on your own. And this one, what is the empirical formula of a compound that contains these percentages of sodium, sulfur, and oxygen by mass? Once again, I will let you do this one on your own. That takes us to the end of this video. Please stay tuned to the next video, in which I'll begin by teaching you how to convert grams of compounds into moles of compounds and then use those amounts to eventually calculate a percent yield. Until next time, my beloved students, have an enjoyable rest of your day.